coming. So I'm going to talk a little bit about problems of sphere packing and energy minimization, and some sort of new breakthroughs that have happened. So at any point, please feel free to stop me and ask questions. I'm happy to draw pictures and explain things as we go along. So I'll try to make this very sort of concrete, and the subject itself is very down to earth and very, has very easy to state problems and hard to solve. But let's see where we get. Okay, so sphere packing in n-dimensional space, that's a problem where we start from. And it's a collection of, so the problem is the following. Sphere packing is just a collection of balls of equal size, which you may as well assume or have unit radius. And they're not allowed to overlap, except they're allowed to have, so in this case they have gaps between them, but they're allowed to touch. They have a point of tangency. But they should not overlap apart from that. And the density of a sphere packing is the volume of the volume fraction of space that they occupy. So that's the density. And the basic problem is find the densest sphere packing, the packing which maximizes the density given the dimension. And there may be more than one. So you start solving this problem as a function of the dimension, and the complexity of this problem goes pretty rapidly. So in dimension 1, okay, ball is just an interval, and you can lay the intervals end to end and cover the entire line, and so you can achieve density 1. Obviously, you can't do better than that. So that's the end of that problem. Okay, so you can solve it trivially. In dimension 2, it's pretty easy to see what should be the optimal packing in 2 dimensions. You put coins in a carrom board or something, you will see that this is the hexagonal or equilateral triangular arrangements that you should have. But in fact, proving this maybe takes half a page or so. It's not completely trivial, but it requires a little bit of thought. And it was only done in 1940. Okay. It's not too difficult, but it's much more difficult than dimension 1. And then dimension 2, dimension 3.
There are no boundary conditions.
Yeah, in this case, we're just looking at the entire space. It's not a container. People do study things where you're trying to pack things in container, but that's in general a harder problem. You have to sort of have the sort of uniformity that you don't have to worry about boundary conditions.
Right. In 2 dimensions, I was wondering, is it that no one raised this problem before 1940, or
no, it was only solved with a rigorous proof in 1940. That's it.
Meaning people had, but there's no rigorous proof.
Yes. I mean, people had some
heuristic
arguments about angles and whatnot, but if you actually sit and write down a proof, you need to look at what happens in a line of balls, and then where you put the next ball and so on, and it requires just a little bit of work. It's not difficult. And then it becomes more difficult in dimension 3, where the best thing you could do is you could take a hexagonal layer of balls, like in the 2-dimensional case, and then you see that in the hexagonal layer you have sort of holes like this one, this one, this one, and so on. So you could choose a set of holes which are an identical copy of the first layer. And so you could choose this, this, and this, and so on, and continue it through, and that's the second layer. But you could also have chosen this one instead. So there are 2 choices for the next layer. So if the first layer you label by A, then the second layer would be B or C, and then the third layer, if you chose B, would be C or A, and so on. So it corresponds to sort of ternary strings with no 2 consecutive things the same. And that's an uncountable, just like in binary strings, you get an uncountable set. There's an uncountable many ways of doing this. They all have the same density. And the fact that it's the best you can do, that's actually a little difficult. That's the theorem of Hales. Required lots of computer calculation, and initially when it was published with the caveat that people hadn't actually checked the proof fully rigorously, which made Hales very angry. And then he just embarked on a project to make a formal computer verifiable proof, which was only I think this theorem was around 98. Then he started a computer proof project, and he only finished it 3 years back or so. Now it's completely, fully, rigorously verified. These are the densest patterns.
There's no simpler proof.
Nobody has found a simpler proof yet. still requires lots of computer checking.
So is it obvious that like the periodic arrangement will be more efficient than a random factor?
No, absolutely. Oh, well, I mean, in this case, you actually get, so of these uncountably many, only countably many are periodic. So most of them are completely aperiodic. However, they do have this periodic substructure of two-dimensional.
No, I'm saying even let's say in 2 dimensions.
Yeah.
Is it obvious that periodic packing is not?
It's not obvious, but you can do the following thing. You can say that periodic packings can approximate arbitrarily closely. So what you do is, suppose you have some packing that's aperiodic, that's very, very dense. What you can do is you can take a large cube or a square in 2 dimensions, and you can take all the sphere centers, all the spheres will completely lie inside that cube. And then you just tile with that set of spheres, and they don't overlap, obviously. And this approaches the density that you would have as the cube becomes bigger and bigger. So you can approach the density of an arbitrary packing by periodic packings, which is why most people focus on periodic packings when they work on this way. That's a good question.
But for periodic packings, you can just go through all the possible periods.
But you're right. That's a good point. So suppose your period was 1, in which case it's just a lattice. Then there is a fundamental domain that you consider, and there's a modular space, and you can try to maximize the function. And in general, if you have n points per period, if you have n translates of a lattice, then you would get some more complicated modular space. But you could still try to maximize the function. But the thing is, n is arbitrary. A priori, you don't know that the period is bounded by 20 for the densest packing. So in general, it's a very, very hard problem to computationally try to solve this. Yeah. Other questions? Yeah, that was a very good question. Okay, so these are, and so you see that dimension 3 was already incredibly harder than dimension 2. And it turns out, till recently, here's an example of, if you do ABC, ABC, you get the face center, the sodium chloride structure that you may remember. And so in any higher dimensions, till very recently, we didn't know any rigorous answers. What's the densest sphere packing? We had some guesses. Most of them came from lattices, which I described a little bit. But until recently, there were no proofs. And in very high dimensions, we expect that the densest packings are likely to be closely disordered. So in your sense, this n, the number of translates, would be very, very large. If you could show that the densest packing was periodic, that n would grow very fast with dimension. That's the expectation. We don't actually have a proof of this. So a lot of things are unknown in this area.
Yeah. In high dimensions, does that logic work of going from 2 to 3 where you took the best in 2 and then say what's the...
So people do make in very, very high dimensions, no. I mean, people don't know. People expect that it's more likely to be disordered, but in sort of lowish dimensions up to maybe 48 or something like that, people have this construction is called the laminated construction. So there are laminated lattices, and they give reasonably dense packings, and some of them we will see, and they're likely to be optimal, but we don't know how to prove it most of the time.
So numerically, there's some Hamiltonian to which this corresponds to the minimum.
Numerically, sorry?
So there's some Hamiltonian for which this is the minimum. There's some energy function you can write which will be minimized by this densest line.
There is a function, it's a Morse function on the space of lattices. It's not really sort of very differentiable, but yes, you can, I mean, that sphere packing density function is a Morse function. And so you can try to optimize it.
I was thinking more of just giving the space an attractive potential.
We can do that. Yeah. So that ties in with the energy enumeration that I'll get to, but it's not a priori a rigorous way to see that you're going to get something that's dense. I mean, heuristically, yes, that tends to give you things which are far apart, and that's what we tend to use when we're doing numerical experimentation. But yes, a priori we don't know that will not land us in some local optimum. So lattice is just a subgroup, of maximal rank in n dimensions, and here are some sort of typical examples. So there's an integer lattice, all the points with integer coordinates. If you only take half of them, or you make a checkerboard containing, half that and half twice, and you take only the of one color, you get the checkerboard lattice Dn. There's a simplex lattice An, which corresponds to is embedded here inside n plus 1 dimensional space. It's the stuff with integer coordinates with zero sum. and there are some special root lattices, E6, E7, E8, which some of you may have seen in your work. Let me just describe very quickly what they are. So E8 is generated by the 8-dimensional checkerboard lattice plus the all halves vector. So if you take the vector which is all coordinates 1/2, then its multiples and D8 will generate the lattice E8, and it shows up in all sorts of things like D theory and string theory and so on. E7, turns out E8 has 240 smallest vectors of norm 2. If you take any one of them, take its common complement, then you get E7. And if you take a copy of hexagonal lattice in E8, so two vectors at 60 degrees, and you take its orthogonal complement, you get E6. So the special root lattices here is a sort of pretty picture of the 240 roots of E8 sort of projected down dimensions. And then there is one more lattice which will show up prominently in the top, which is the Leech lattice. So here's what I call a zero knowledge definition. Yeah.
Can you go back to the previous lecture?
Yeah. This one? The picture?
Yeah, no, the previous
the
one.
definition, yes.
These lattices are still in some Euclidean space, right?
Yeah, so
special lattices.
The space is the subscript of the lattice. So E6 is in R6 in 6-dimensional space, E7 is in 7-dimensional space, and so on.
So in what sense are they different from each other? Are they different?
They're different. So I'm considering them as, so if you have two different lattices, as groups you can transform from one to the other. But here there's a norm on them. And so in that sense, there's no isomorphism taking one, like for instance, D8 and E8, there's no isomorphism of lattices. So there's no map, which is, group theoretic isomorphism, which also makes the norms equal to the norm of the image for everywhere. So with that norm condition itself, yeah. Okay, so I was just about to give you a zero knowledge definition of the Leech lattice. So the Leech lattice is 24-dimensional lattice, which is even, which means all its norms are even integers. It's unimodular, so its fundamental domain has volume 1, and it has no roots. So since we said all its norms are even, the norms are 2, 4, 6, or 8, and there are no vectors of norm 2. So those are the roots. So it has no roots. And this characterizes the Leech lattice up to isometry in limit 24. If you want a more concrete definition, there are lots of constructions of it. The usual one involves what's called the extended Golay code. Conway-Sloan's book on sphere packing lattices and groups gives 23 constructions of the 24-dimensional Leech lattice. Just kind of cute fact of Niemeyer lattices. My favorite construction is the following, which if you like Lorentzian space and string theory, you might like. So if you look at the lattice 2 sub 25(1), this is the lattice that's in 26-dimensional space-time, which has this quadratic form. Is generated by all the integer vectors or all the half-integer vectors with even coordinate sum. So that's 225(1). We're going to do something to it. So there's a y vector w, which is this vector 0, 1, 2, 24, 70, and it has norm 0 under this norm because of this identity 1 squared plus 2 squared, this is 70 squared. That's the maximum number, by the way, for which you can write such an identity. Consecutively, all the numbers of the sum number equals something squared. And the Leech lattice, so okay, this thing has pairing 0 with itself, so you take its orthogonal complement, gets you down to 25 dimensions, and you mod out by itself because it's orthogonal to itself. That gives you a positive definite lattice. That's the Leech lattice. Okay. Anyway, that's an actual construction. Alright, so given a lattice, there's an associated sphere pattern, which is you make the spheres as large as possible, centered on the points of the lattice. And that distance is a radius, the radius has to be the minimum vector length of the lattice divided by 2. That's as much as you can cram.
Sorry, about the Leech lattice, isn't there a construction involving 8 lattices?
You can get from the 8, yeah, you can take 3 copies of the 8. Yeah, so that's one of the Niemeyer constructions. So the 23 constructions, I believe, they come from the Niemeyer lattices, and those are all the sort of, evenly modular lattices in 24 dimensions. So you can start from A1 to the 24, or you can start from the 8 cubed. But yeah, I didn't want to do that one. So okay, so you can restrict the packing problem for for lattices, you can say, I'm not going to look at all the sphere packings. So, in your example, so you don't want to look at n translates of a lattice, just one translate of lattice, namely the lattice itself. And you can say, okay, this easier problem can be solved. And it turns out you can solve it algorithmically. And there is a theorem due to Kohlken and Zorotarev, which lets you determine all the local optima for density, in the space of lattices in dimension n. But the number of local optima grows really fast. So in principle, that algorithm is hard to pursue and to implement. So these turn out to be all the answers that we can actually write down. So up to dimension 8, this was known around 1930 or so. Whitfeld had a paper which finished off 6, 7, and 8, and then we had Henry Cohen and I had a paper which did dimension 24. We also got a different proof for the 8-dimensional case. But for instance, in 9 dimensions, there's a computer program that some colleagues of mine have been running for several years now, and it is not finished. So this is one of those problems that's algorithmically very hard to finish.
And so this is so the distinction here is that you just take the lattice and then assume that amongst the space of these lattices, if you just pack them,
right? You're only allowing this regular packing. So you're not allowing lattice and sub-translates of lattice. Yeah, you're not allowing that. You're only allowing this regular configuration.
And with this sort of n lambda by 2 kind of.
Yeah, exactly. I mean, this is the maximum that you could do.
So I see. And so then it's a finite problem, and you search over that. And
that's, well, I mean, even the bad algorithm is somewhat more clever than that. I mean, first of all, you have to figure out what the local optima are, and that requires some refinements. But even enumerating on the local optima, it's quite difficult, right? But I mean, the way we did this in 24 dimensions was certainly not using that algorithm. I mean, we started off from the Leech lattice, and we had various sort of geometric and combinatorial things that we could prove, and some of these things involved the linear programming bound that I'll talk about, which allowed us to show that was the densest lattice. Other questions? So here are the new results. So now the result is this: the theorem Viazovska proved in 2016 is that the E8 lattice packing is not just the densest lattice packing, but it's the densest sphere packing in 8 dimensions. Okay, so we don't know the answer in 4, 5, 6, 7, but we know the answer in 8 dimensions. And then we followed up about a week later, in joint work with her, where we showed that Leech lattice is the densest sphere packing in 24 dimensions, not just the densest lattice packing. And there are 2 main ingredients to the proof: linear programming bounds for packing, and the sort of newer ingredients is the theory of modular forms. So I'll say a few words about this depending on time.
Can you say a little bit about the expectation? I mean, just from numerical experience, what do we expect for other dimensions?
Yeah, that's a good question. So, right.
Is the densest packing?
So in 4 dimensions, so in 4 through 7 dimensions, we expect that those lattices are in fact the densest. We can't prove it yet. And 4 may be the easiest dimension to prove, but we don't know a way to get there. Beyond 4, so interesting things start happening in dimension 9 and beyond. So in 9 dimensions, the best lattice known is the laminated lattice, called lambda 9 in 9 dimensions. And it has the weird property that you can split it into a sublattice of index 2, and it's one coset for it. And so let's color these balls black and one coset white. And so it turns out that you can translate the white balls arbitrarily long distances without ever overlapping with the black ones. So that feels like the kind of absurd situation where you ought to be able to cram in more spheres, but nobody's found a way to do it. So, and in fact, nobody's found a way to improve on that lattice either. So there's a continuum of packings that has the same density as this lattice packing, but there's no proof that nothing is better. And in 10 dimensions, it gets even worse. So in 10 dimensions, the best known packing is not a lattice, it's 40 translates of a lattice. It's called the best packing because Mr. Best, who was a coding theorist, discovered this stacking. Anyway, the best packing, the fact that the best packing is not a proven fact. And so if we could implement this algorithm, for instance, to show that the densest lattice is what we think it is in 10 dimensions, then we will be able to show that the best packing is at least better than the best lattice packing. But we don't know that.
Are there bounds known from 4 to 7 dimensions and are they close to?
Yeah, so there are linear programming bounds, and I'll say a few words about them. You can write upper bounds and lower bounds, but they don't match. The only cases where they do match are these 8 and 24 where they miraculously match. And so there are bounds known, but there's no sort of rigorous right answer. No, you don't have it.
Nothing.
Go ahead.
Nothing special happens in 16 dimensions.
In 16 dimensions, there's what's called the Barnes wall lattice. I mean, there are some special lattices in other dimensions. In dimension 12, there's the Cox-Retord lattice. In dimension 16, there's the Barnes wall lattice. In some other dimensions, 48 and 72, there are other extremely even modular lattices. But we don't have a clue of how to prove anything about them. Yeah. I mean, we don't expect necessarily that they will be the densest. That's the situation.
What are the densities you actually achieve here?
What is the density?
What is the density?
Oh yeah, I never write these things down. But yeah, in E8, the fundamental domain has volume 1. I mean, you normalize it, and the minimum distance is square root of 2. So you get square root of 2 over 2 to the 8 times the volume of the 8-dimensional unit ball, which is something involving a gamma of it. You can write it down, and yeah, that's what it works out. So you can write it down. It's some I don't know offhand, but I can tell you one thing, which is if you write down the density of sort of asymptotically, what do you expect as doing? Yeah, it goes to 0. It goes to 0 exponentially. That exponent we have upper and lower bounds, but we don't even know what the exponent is in general. Yeah.
On the space of unimodular lattices at dimension n, did you say that density function is not a continuous function?
It's a Morse function. It's a continuous function. Yeah. It's a continuous function. It's just that it's not sort of one of those infinitely differentiable functions. But you can basically work with it.
And then is the supremum or infimum realized on this space?
Yes. Yeah. You can show that the supremum of the density function is realized. The infimum is 0, so it's not actually realized.
And do we know which points realize the supremum?
That would be nice to know. That's what the densest lattice packing is. I mean, the question is, right, the Hermite problem. How do you solve the Hermite problem in dimensions? That's basically the question, which points realize this supremum in dimension n. In general, we don't know. We know it in dimensions up to 8 and in dimension 24. Those are the only examples where we can solve the lattice packing problem. So it's equivalent to it. Other questions?
Within these dimensions which are known like 8 and 24, is it expected that the other packings are local, other lattice packings are local extrema?
Oh yeah, I mean, there are many packings you can write down and you can show that they're local. So there is a criterion.
But the other lattice packings?
Well, no. Oh, you mean our lattice packings in general local extrema
amongst the space?
No, that's not true.
It's not true.
Yeah, it's not true.
So locally, you mean can you move the spheres a little bit?
Right. I mean, you can, the way I construed your question is, you can move it, or if you think of a lattice and you consider it as n translates of a lattice, where you just take some sublattice of this of index n, you get n copies. And the question is, in that space of n translates of that sublattice, which is some space of periodic occupations, is this thing locally optimal? The answer is, in general, that's not true for every lattice. Yeah. But you can show some things, like if something is local, like I believe you can show that if a lattice is locally optimal among the space of lattices, then it may be locally optimal in such a thing. But every such is Alright, let's keep going. So here's one more thing that I wanted to say, which is there's an energy minimization question which seeks to find the optimal configuration of points which minimize potential energy. And if you're a physicist, this might be way more interesting to you. So very formally, what you would try to do is, I'm going to look at, some potential function f, which is a function of distance. So it's a function on positive reals to the reals, and let's suppose it's sufficiently rapidly decaying, so you can sum it over things. And so I'm going to look at periodic configurations. You don't have to, but then I'd have to write things like lim for lim soup, and I don't want to. So let's just say something is periodic. And so it's a discrete set stable under translation by some lattice. So it's an n copies of some lattice, or k copies of some lattice for some k. So we're going to define its potential energy by the following thing. Okay, so the first thing that comes to mind is just take all pairwise distances and add them up, add f of that distance up. But the problem is you're going to count every distance infinitely many times, right? If x and y are in the configuration, then for every lattice point lambda, x plus lambda and y plus lambda are also going to be in there, and their distance is the same as x and y. So everything you're going to count infinitely many times, so this will obviously diverge if you just do it the sort of naive way. And so what you have to do is you have to normalize. What you do is you take some large ball of radius capital M, you take all the pairwise distances, and you divide by the number of points in that ball, and this normalizes so that every distance comes exactly once, you take the limit of almost. And if you're a physicist, you probably want to attach half to this so that you don't have x, y, and yx. But if you're a mathematician, you may not care so much. Okay, so, right, that's the definition of potential energy. And the problem is the following. It says, given a potential function f, find the infimum of this potential energy as C ranges over periodic configurations of a fixed density. So you have to fix the density of C in order to just stop all the points from escaping to infinity. By if you just scale, any configuration, the distances get larger and the function is decaying. So, if the scaling becomes larger and larger, you're going to get zeros, not what you want. So you fix the density to be 1, let's say. And if it's attained, you have to determine. So this is a family of problems, one for each potential function, and this is obviously a much harder sort of setting than just sphere packing, trying to find the minimum potential energy. This is a problem that physicists would like to solve.
So is there some assumption about positivity of f?
Yeah, we're usually going to assume that f is positive. I didn't state that, but sure.
But if f was allowed to be both positive and negative, you wouldn't need this condition of fixed density. You might find equilibrium points where.
Yeah, yes. I'm only going to look at functions which are positive. You could try to state it in broader generality, but I think you will get sort of pathological behavior if you don't fix the density in general. Although people do consider things like Leonard-Jones potentials where you're allowed to dip below 0 and you still get a.
The density should be fixed by maybe that's what the wrong intuition.
That's true in your setting. I think if f has local minima like in Leonard-Jones or something, then I think there's exactly one scaling which is allowed, but not in the setting we're going to consider where things are sort of always positive and decaying or something like that. Then you really don't want them to escape to infinity because that's what they're going to do. If it's a positive potential function, there's no attraction whatsoever, they will allow them to.
I thought he was meaning also something like sodium chloride, where you have positive, negative, positive, negative.
Ah, yes, yeah.
Oh, that also.
Oh, that's a way more complicated function than this.
Yeah.
So this family of problems is of interest in mathematical physics. It's also a generalization of sphere packing. Let me explain why. So you can try to minimize, for instance, the inverse power law potential functions, which are just 1 over distance to some power s. For s bigger than 0, you need s bigger than dimension for things to converge. So let's assume that s is bigger than dimension. If s goes to infinity, what happens is you recover the sphere packing problem. Why is that? So if you look at 1 over if you look at potential energy for a periodic configuration, the smallest distance is going to give, let's say it's R0, is going to give you 1 over R0 to the S. So you get the average number of points at that distance divided by R0 to the S. The next one will give you R1 to the S in the denominator. And the thing is, R0 over R1 to the S is, R0 over R1 is less than 1. You're raising it to some exponent which is going off to infinity, so that term will not contribute at all. And so the dominant term tends to be only the stuff from the nearest neighbors. So the question just becomes how many, what's the smallest distance R0 that you have, and that is the sphere packing problem. And it's in fact a little finer than the sphere packing problem because it also says what's the average number of neighbors that you have. But let's just say that the sphere packing problem is included in the limit of energy minimization. So, and let me also note that these things give interesting mathematical invariants. Like if you're a lattice, this potential energy is basically an zeta function of the lattice. And if you have a Gaussian, then you get a theta function of the lattice evaluated point on the imaginary axis. And so that's the theorem that we're going to talk about solutions of the energy minimization problem. That's the sort of new work. I'll just probably mention that and sort of talk about the main ingredients. But let me say a few words about intuition a little bit. So both of these are geometric optimization problems, sphere packing and energy minimization. And you can ask them in a sort of easier setting, namely the compact setting. So I've stated them in Euclidean space with infinite number of points, but you could do this on the sphere. So for instance, you could have, so there you always consider finite sets of points because you're compact and you separate by some distance. That means you can only have finitely many points, so that's code. And you try to minimize geometric or physical quantities such as the minimum distance or the overall potential energy while fixing the number of points. And it's much easier to solve than the Euclidean case. So let me just give you a couple of examples. So as Surat was saying, if you want to put n electrons on the surface of a sphere and you want them to repel under electrostatic potential, this is Thomson's plum pudding atom, model of the atom, then you might actually you might run that simulation and that will give you a good spherical core where points are separated by a reasonable distance. I wanted to show you a simulation that I actually coded up at one point. So you can see, if I put down 12 points and they evolve on the surface of a sphere, you see that they will converge to a regular icosahedron. This doesn't happen this doesn't happen for arbitrary number of points. You're not going to see some nice regular polytope in general, but for 12 points, you get this nice pretty picture. Okay. So when they come to equilibrium, you expect them to be far apart, form a good spherical core. And so you can use this energy minimization to heuristically get good spherical cores. And similarly, in Euclidean space, you can try to get good sphere packing in space. And again, you can sort of write down the energy function. This should be not a complex number C, but a script C. For a spherical core, you can write down its potential energy this way. And the basic question there is find configurations of, fix the number of points and find the configuration which minimizes potential energy for any given potential function. And if you choose F appropriately, then the global minima turn out to be good spherical cores. And you can get them, just as I showed you, by sort of gradient descent on the space of configurations. And so here's a good natural class of potential functions. They're completely monotonic functions of square distance. So what does this mean? So if you write the potential function as a function of the squared distance rather than just the distance, so g of r squared, then you want g to be positive, increasing, convex, etc. And so the derivatives should alternate in sign. And this is something that is actually fairly natural in analysis. People study completely monotonic functions. But it's still strong enough to, there's a broad class of functions, it's still strong enough to allow us to prove something. In the compact case, the cone of such functions is spanned by these functions, AL, which is 4 minus the distance squared to the power L, so non-negative L. So why 4? Because the squared distance, maybe I should have said, yeah, so the squared distance between antipodal points is 4. Okay, so if you try to run this program for small numbers of points, what do you get? So if you do this for 2 points, it will give you 2 antipodal points. You do this 3 points, you get an equilateral triangle on the equator. 4 points, you get a regular tetrahedron, beautiful. 6 points, you get a regular octahedron, very nice. You notice that, you may have noticed that I skipped 5 points. Okay, so what happens with 5 points? Okay, so something interesting happens. So you get two competing configurations. So one is what's called the triangle bipyramid. You've got the north and south poles and an equilateral triangle on the equator. This is just one configuration. And the other is a family of configurations depending on the latitude. So you put one point at the north pole and one square somewhere on the southern hemisphere at some latitude. And then that latitude is theta, and so you get a family of configurations depending on the height. Okay? And these compete. You see it, what happens is as the sort of potential function, if it's an inverse power law, if it goes to infinity, these tend to give you at least local minima, and this square moves up to the equator, and they both have the same minimal distance. So as spherical poles, they're basically equally as good, but for energy they compete. So here's what happens. So for these functions, the first configuration, triangle bipyramid, wins for small exponents, and the square pyramid wins for large exponents. And similarly for inverse power laws. And you can actually, but when I say wins, it's just between themselves. To actually show anything rigorously as a global optimum, it requires a lot of work. And there's some work by Richard Schwartz at Brown, just showing this for 1 over r and 1 over r squared. It's already a lot of computer calculation. That's a global optimum. So in general, what happens is for a family of potential functions, you get a family of optimal configurations. I just want to give you one more example. If you put 8 points down, you might think that you get a cube, but in fact, that tends to be unstable. What you get is a skew cube. So you've got two square faces, but they're 45 degrees to each other. And the distance between these two square faces makes it you can vary that distance. It's an entire family of configurations. And which one wins depends on the potential function. That's typically what happens. There's no one pole which is going to win, which is going to minimize potential energy for every potential function that you write down.
So Physical proof is a global minimum. It's 8 for 8 part.
Yeah, well, they're global, we assume they're global. It's not proven.
Just from the numeric 60.
Yes, exactly. So we define something as universally optimal. Oops. So you say a spherical pole is universally optimal if it minimizes everything in sight. So everything in sight being all potential functions which are completely monotonic, or functions of square distance. And there are examples. That's the amazing thing, that there are things which are universally optimal. Typically, you're not going to see stuff. But we saw some examples like in the antipodes and the 3 points and 4 points, 6 points. The existence is very uncommon, but here's a list that Henry Cohn and I showed that consists of universally optimal poles. So they optimize pretty much everything you can throw at them. Here's an example of one of those universally optimal configurations. This is a regular polytope called the 600 cell in 4 dimensions. It's just a projection of that. So these configurations are all universally optimal, the ones that I listed. And the idea of proving something like this is that that linear programming bounds the potential energy, and they turn out to be all sharp for these configurations. They match their lower bound. And since our work, there have been more examples given of universally optimal poles in other compact spaces like projective spaces, Grassmannians, Hamming space, and so on. But so far, till recently, there were no examples of things in non-compact spaces. So that's what I'm getting to. So in the Euclidean case, again, we expect different, periodic configurations to minimize different potential functions. For instance, if you restrict to lattices even, then there is a Poisson summation identity which relates the F potential energy of a lattice and its F hat and its sort of Fourier transform potential energy of a dual lattice. So if lambda minimizes F, then you'd expect its dual to minimize F hat. And so you don't expect, unless lambda is equal to it's isometric to lambda dual, you don't expect that it would even be universally optimal. But we conjectured that these 3 lattices, the hexagonal lattice in 2 dimensions, E8 lattice and 24-dimensional Leech lattice are universally optimal. And now for two of those cases, the supposedly harder ones can actually show that. So in the two-dimensional, let me just say that's kind of appalling that the two-dimensional case we cannot show, but it's more complicated for various reasons that I can explain to you later, that two-dimensional case is actually harder than the E8 and the Leech cases. So anyway, the theorem is joint work with Henry Cohn, Steve Miller, Radchenko, and Viazovska, is that these things are, the E8 and Leech are the universally optimal. So in fact, they optimize all completely monotonic functions for distance. Okay. Any questions so far?
So what led you to make this conjecture? This was long before this proof, right? So what?
When did we make this conjecture? I think around 2007.
Yes, what motivated us?
Oh, what motivated you?
How did you guess that it's,
No, we did. We had numerical, experimentation. Computed potential energies with respect to periodic configurations, with respect to lattices, and so on. And it just looked like these things were really.
And so universal optimality is something which is very special to
It's
these
very special,
dimensions, you think, or
we don't. I mean, we have not guessed any kind of analogs anywhere else. I mean, we can't think of any other examples in dimensions where, in other dimensions where universally optimal. It was something that was quite special, but it will tie in. I mean, the proof of this. I'll explain some ideas of the proof, and it will tie into things which perhaps could be extended to other dimensions. Oh, this is the picture of all of this. That's Henry Cohn, that's me, that's Steve Miller, then Radchenko, that's Marina. Okay, so here's the first ingredient, the linear programming bounds. So I'm going to normalize the Fourier transform of function as so, and then here is the linear programming bound for sphere packing. Okay, so suppose you have a Schwartz function with these three properties. So f and f hat you normalize to be 0, and you assume that f is non-positive for all vectors which are bigger in norm than some r, bigger in some real number r, and f hat is always non-positive. F hat is non-positive over here, f hat is always non-negative. Then you get a bound. So given this input, given such a function, you get a bound on the density of any sphere packet. Okay, that's the density of any sphere packing dimension is bounded out by the n ball of radius, the volume of the n ball of radius r. That's the bound that you get. So the r comes in from this. That's the thing. Okay, so let me explain.
What's the I didn't understand the statement at all.
Yes.
So I didn't understand the statement. What I would explain.
Right, it's kind of magic. It's a very easy proof, and I'm actually going to give you the proof. But the idea is the following: the sphere packing problem, you can try to sort of write down. You can try to reduce part of it to something involving. If you only look at the distances that show up among pairs of points, right? Then you can try and forget all other geometric information like triangles and so on. If you only look at 2-point functions involving the sphere packing, then it becomes some question in an infinite dimensional space where you're saying, you got this delta distribution of distances, right? And you're trying to optimize some function on the space of distributions. And if you write down the dual program that's what ends up being the linear programming bound. This is in some sense the dual program of, there's a dual linear program, that's where it ends up being, that's the LP bound. It's a, space on, you get a function on, you get some objective function on a space of functions, and that gives you a bound. But we'll see it when we write down the proof logical, so it'll become a little more clear. So the first thing is, why is it called a linear programming bound? So we can rephrase the theorem by scaling f. So if you have an f of r, you can consider scaling as follows. So you can look at alpha f of beta r. So you can scale the argument and scale the function. And this allows you to set whatever value you want for the function by scaling the alpha, and also whatever value you want to scale the function, to scale the Fourier transform at 0 by scaling beta. So I'm going to scale it so that f hat is 0. I'm going to scale it so that f is non-positive for x bigger than or equal to 1 rather than bigger than or equal to r, and f hat is non-negative for all t. Okay, that's the only thing I'll do. And then it turns out that then it says the density is bounded by, then f of 0 comes into the objective function. So 2 to the minus volume of the n ball times 2 to the minus n times f of 0. Okay, so, and if you now look at this, what this is saying about f is the Schwartz function, some infinite dimensional space of functions. These are all linear constraints on f. I mean, there's a continuum of linear constraints, but they're all linear. And the objective function is also linear, so it's a linear program. It's a convex program to be more precise, but you just say it's a linear program. Okay. And I'm just going to show you what the proof is for lattices. So if you have any lattice, suppose we scale it so that the minimal vector length is 1, because density of the lattice does not depend on the scaling of the lattice. Then you can write out the Poisson summation formula for f with respect to this lattice. It says if you sum f over all the lattice points, that's equal to the sum of f hat over all the dual lattice, except you have to scale by the fundamental volume of fundamental domain, the full volume of lambda. Okay, so now if you see what's happening, f is set up so that whenever x is not 0, the vector length is at least 1, which we assume, but f is then non-positive. So the only positive contribution that comes over here is from f of 0. So whatever this thing is, it's less than equal to f of 0, and whatever this thing is, it's greater than equal to f hat of 0, because f hat is always non-negative. So this tells you that f of 0 is greater than equal to the co-volume of lambda, because f hat of 0 is scaled to be 1. And that immediately tells you the volume of, because we assume it has minimal distance 1, the ball that you fit is radius 1/2, and so you will get this power. So that it's basically a one-line proof of the linear program now. But it tells you what constraints f and f hat have to satisfy for this bound to have any chance of being sharp. Right? So if you want this bound to be sharp, then you need f to be 0 at all the vector lengths, and f hat to be 0 at all the vector lengths, apart from 0. So let me skip over some of this because we are getting close to the end. But you can write down this linear programming bound as a function of dimension, and you see this is one of the previous best upper bounds, the red line. This is the Cohn-Kumar-Miller-Radchenko-Viazovska linear programming bound, the green line, and the blue line, the jagged thing, the blue curve is the density of the best packing node. And so you see that it seems to at least agree in dimensions 2, 8, 8 is here, and 24 seems to agree with this. And in fact, it does exactly agree. That's the theorem now. But here's what we needed to know of the functions, that f, suppose we wanted to show that the E8 or the Leech lattices were actually the densest sphere packings, as in Viazovska's proof or our generalization of it, then we would need f to vanish to order 1 at the smallest vector length, which is square root of 2, and we need it to stay below the axis after that. So it has to be non-positive. So it has to have double zeros at all the other vector lengths, square root of 4, square root of 6, and so on. And f hat has to have double zeros at all the vector lengths. So these are the sort of simultaneous constraints that f and f hat need to satisfy. So these are these magic functions which we somehow need to come up with if we want to show E8 and the Leech lattice are the densest. And in the paper where we did the lattice packing, we approximated by using some very high degree polynomial times the Gaussian to show that we could get very, very close to the density, to the Leech lattice density, up to 10 to the minus 30, and similarly you could do it for E8, but we couldn't get exactly there. On the exact function, we want to show it the full thing. So we were stuck for a long time, and then
so you used you tried to fit that
exactly.
Yeah. You just put some arbitrary
We
coefficients and then try to ensure that it's 0.
We actually did gradient descent and then Newton's method on the locations of the roots. We set the roots to be close to, but I mean, we had something which incrementally went up with the number of roots. We had an algorithm which said, let's start with 3 roots. You put optimize what you could get and go up to 4 roots with these 3 roots as a seed and then so on and so forth. So we went up to 200 double roots or so.
If you just do gradient descent with this 1 over r ds potential,
yes,
that is much more efficient than this.
Well, but
we just put the spheres together and just throw some spheres and beat them. smaller
Well,
argument.
in this case, the thing is we know what the answer is. Right? I mean, usually you do that to figure out what the code should be. But here, here we were actually trying to find these functions. So right, so Viazovska actually came up with a magic function, and it used modular forms. And should I try to wrap up with?
No. I think we are quite flexible.
Flexible. Okay, so I'll try to sort of give a little bit of an overview of what these modular forms are and how they got used in this function. But I'll try to be brief. So modular form very roughly is a function with a lot of, on the upper half plane, with a lot of symmetries. So namely, if you look at 2 by 2 integer matrices, they act on, or even real matrices, they act on the upper half plane by this sort of picture. So if you have a matrix A, B, C, D, it is going to act on an element of a complex number Z by taking to AZ plus B over CZ plus D, that linear fraction transformation. And we say that a function is a modular form if the function at this image transforms nicely. So f of AZ plus B over CZ plus D for every matrix in SL2Z, in the integer 2 by 2 matrix in the determinant 1, is transformed by CZ plus D to the K when you apply this transformation. Okay, so that's modular form. And it turns out that these modular forms have Q expansions. So they have a Fourier. You can write down. How should I say this? So it's some function. So f of z is a modular form, satisfies that transformation property. Then the point is, if you look at f applied and apply that matrix, then that will tell you that f of z plus n is the same as f of z. Okay, because that transformation factor turns out to be 1. And so this tells you that f of z you could write down in some kind of Fourier basis as sum of a n e to the 2 pi I n z. So this is what's called a Q expansion. This is just Fourier series for this function with respect to the x variable. So right, that's what I'm writing here. So there's a power series expansion, and the modular form says that this expansion should not have any negative terms when you write it down. So at infinity, it should not blow up. And similarly, in general, you have what are called cusps for a group for SL2Z. It should not blow up at any of the cusps. That's the condition for modular form. If it's only a Laurent series, so if you're allowed to blow up, but only to some finite degree, there's some finite pole, finite order pole, then that's called a weakly holomorphic modular form. So that's one generalization that we need. Modular forms that show up are weakly holomorphic, not necessarily fully holomorphic. And the other generalization that we need is that they have to be quasimodular, which I'll get to in a minute. But if you want to write down examples of modular forms, the simplest way is to take some function and you symmetrize with respect to SL2Zs. For instance, you symmetrize 1 over AZ plus B to the K, you get what's called the Eisenstein series. And here are sort of two typical examples, E4 and E6, which actually generate all the modular forms for the full modular group. And there's a famous sort of discriminant, modular discriminant, which is if you take a suitable linear combination of these, cube this and you subtract the square of this, divide by 1/728, you get a beautiful product expansion of this modular form. And there are other sources of modular forms. For instance, if you have a lattice, you can take its Theta series. You can take the sum over all vectors in lattice of q to the norm of v over 2, and that gives you a modular form for some convex subgroup. So for instance, you can, from the E8 lattice, you can get the Eisenstein series E4 that we showed you in the previous page. And also classical theta functions, which are these theta null vertex, which arise in the study of abelian integrals and abelian varieties, theta 0, 0, theta 0, 1, and theta 1, 0. And if you take fourth powers of them, you get modular forms of weight 2 for this common subgroup gamma of 2, and they're related by Jacobi's identity that the sum of these two equals this one. Okay. These are all the modular, almost all the modular forms that we need. We need one more, which is E2. So if you apply the Eisenstein series construction to weight 2, it doesn't quite converge, but you can make it converge. The only problem is, and you get this Q series. The only problem is it doesn't transform properly when you go to z goes to minus 1 over z. You don't quite get just z squared equals z, you get this extra error term. And so if you look at the algebra that this generates with normal modular forms, that gives you what are called quasi-modular forms. And you can also get it by differentiating modular forms. And this is sort of things that people have been studying a lot recently with quantum modular forms and modular forms and so on. So I'm just going to give you describe where the magic functions come. They come from Laplace transforms of modular or quasi-modular forms. So in particular, I'm going to tell you how to make the function for 8 dimensions. So if you take this quasi-modular form, E4 E2 minus E6 squared divided by delta, so this is weakly homomorphic because it's got a pole because of delta, and it's quasi-modular because it's got E2. And you take its Laplace transform. So here's the modular form. You multiply by essentially e to the pi r squared z dc. You take contour integral from 0 to I infinity. So that's a Laplace transform with respect to the variable, r squared. And you multiply this into 4 sine squared pi r squared over 2. So let me just say one thing about the function outside, which almost gets you all the way, which is one of Farina's insights, which is that this function 4 sine squared pi r squared over 2, what does it look like when r is the square root of an even integer? R squared is an even integer, so this thing is just a multiple of pi, and so sine of it is 0, and sine squared has a double 0 there. So this function just, and it's evidently non-negative, so this is almost what we want, except for the function f, except what we wanted was a function which had a single 0, right? And also had better this also doesn't decay, but it's got some of the good features of the kind of function that we want. We want something which has a single 0 at the first one, at square root of 2, and double zeros everywhere else, and also we need it to decay properly. And also, we need its Fourier transform to be well behaved. And so, what this ends up doing, this kind of integral, first of all, you get a pole from this integral. You get a single pole at the first 0, and that makes it a simple 0 rather than double 0. The second thing that you get from being modular is you get something called the Fourier transform. So if you take a Fourier transform, what happens is this thing becomes, if the pi r squared z, its Fourier transform takes z to minus 1 over z. And so there's a way to write this so that it doesn't have any 4 sine squared pi r squared over 2. It's a combination of 3 integrals which just involve modular forms times e to the pi r squared z dz. And they go under the Fourier transform, they essentially take z to minus 1 over z. And that's where sort of the modular form property is getting used to give you something reasonable. Yeah.
The minus 1 over z is the argument of phi naught, or it's a set?
Oh yeah, this is phi naught evaluated minus 1.
Yeah, that's it. Yeah. So then you said there's a pole at z equals 0.
You get a pole at, well, this integral turns out to have a pole at r equals square root of 2. So let me say it on the next page. So if you look at, c equals it, you said c equals it, you get phi naught of I over t times t squared. And so that thing has an exponential growth. And so, so you get e to the pi r squared t minus pi r squared t plus 2 pi t. So you get an r squared minus 2 showing up there. And that goes in the denominator. So what that does is give you a simple pole, and that downgrades the double 0 to a single 0. That's the first thing it does. Yeah.
So I'm going to ask a double question because I'm missing. when you initially get this proof about densest sphere packing interpolation function and then its Fourier transform, I thought the function had to be in the same number of dimensions as the sphere packing problem you were trying to solve.
That's a good point. Yeah. So I think I must have glossed over at some point, but you can assume that without loss of generality, it turns out you can assume the function is radial. So it's only dependent on the radial distance. You can write it as a function of the length of the. It doesn't give you any loss in the bounds.
But then where does the dimension enter here? Where does the dimension?
So the function that you plug in, it would be so.
Oh, because in the Fourier transform you're saying there's an R.
Yeah.
I'm just saying the function is radial, but the Fourier transform still remains.
The Fourier transform, it turns out, has some dimension coming in. Exactly. Right. So that's where it enters. So that's what modularity gets you. It's sort of the Quasimodular property tells you that first of all, what you do is you replace this thing by a sum of three integrals which don't involve this sine square thing in front. And I'm not going to go through the details of how you do that, but they show up. Basically, it turns out by shifting contour integrals, you can absorb them into this I to pi r squared z. And then the modularity property tells you that basically what you're doing when you do Fourier transform is replacing this by z to the minus 4th pi r squared minus 1 over 3. And the 4 is e to over 2. That's where dimension is coming in. So then you use the transformation properties under this, and the fact that it's Quasimodular tells you it's doing something reasonable under the Fourier transform. That's what you use to show that the Fourier transform has the right property. And similarly, I almost repeat as similar to the Laplace transform. This one, by the way, tells you it's an even eigenfunction. So the Fourier transform makes it equal to itself. And the other one is an odd, involves the u, v, and w I talked about. That gives you an odd eigenfunction. And then what you can do is you can combine them just to make the right values and derivatives at the initial points. And then that's it. I mean, that basically is the function that you need. Let me just, the last thing I'll say is how did Viazovska come up with this idea of having quasi-modular Euclidean form? So it turns out if you make this ansatz that it is 4 sine squared pi r squared over 2, which is reasonable because it has reasonable zeros, times some function, times some Laplace transform, you have to make that leap of faith. Once you do that, it turns out that the transformation properties required basically force it to have some depth. Depth of a quasi-modular form is the highest power of E2 that shows up. The weight is the weight of a modular form, like I talked about, and the power of delta is dictated by the growth of this function, and they're all pinned down once you write down your answers, and you require some reasonable properties for the Fourier transform. So that fixes this dimension, the space of modular forms, and once you fix the space of modular forms, that's a finite dimensional space. And some extra conditions with the decay properties basically specify uniquely of the scale. So there's a unique thing which does it, and you can pin it down once you make the right answers, which is.
Why was dimension 8 and 24 important then? Why doesn't this work in other dimensions?
I mean, in principle, you could try to do it in other dimensions. So our guess is that you can use modular forms to get asymptotically better bounds, and certainly better bounds in low dimensions. But we haven't done that yet. I mean, that's something that will happen in the near future. But you won't get anything. You may get asymptotic improvements. You won't get anything sharp. That's our guess, because the fact that these things tend to be sharp is a function more of the lattices than of the bounds. The bounds is going to be some smooth curve, and you saw this jagged, the lattice curve was not some smooth curve, right? I mean, each dimension has its own sort of peculiarities, and so you don't expect something very smooth, at least in low dimensions. So, you're probably not going to get exact bounds for any dimension beyond these, but we don't know for sure.
So modularity, essentially, the role it plays is in making it to be a Fourier eigenfunction.
Exactly. Yeah.
But the fact that it's a Fourier eigenfunction, that's not strictly necessary in your original approach.
It's more or less equivalent. Yeah, the thing is, even Henry Cohn and Noether, when they did this calculation, they could reduce to Fourier. So the first simplification I was telling you about is that you can assume it's radial. And then what you can do is, if you have any function that you want to plug into the linear programming bounds, you can always decompose this sort of f plus, f hat over 2 plus f minus f hat over 2. So, and this is a positive eigenfunction, negative eigenfunction. And it turns out that, if you want to impose reasonable condition on f of any quadratic of the sort, that it's enough to essentially get something about the negative eigenfunction. So the eigenfunction, the eigenfunction decomposition essentially tells you everything. It's more or less equivalent which one, if you work with a full function or with the eigenfunctions. And it turns out this is nicer. You see the types of functions that we saw were quite different between even and odd. In the even case, you always saw things for the full modular group, but you saw Quasimodular forms. In the odd case, you saw genuine modular forms, but you saw for the congruent subgroup. And that persists when we do energy minimization. I won't really get to it much, but I want to say one or two words about that next. But roughly that's the idea of how you come up with these magic functions. So any questions so far? So I'll just say a couple of things about, so Leech is similar, let me just say, and then it turns out, right, here's the one thing I want to say, that something very general happens in the energy minimization case. We prove universal optimality through a Fourier interpolation formula, and I wanted to state that. And so what happens is when you try to prove universal optimality, you again have linear programming bounds. And this time they say that if you're given a potential function f, that there is an auxiliary function, just like in this case there was an auxiliary function f, here we're calling it h. H is less than or equal to f for all x, and h hat is non-negative for all x. Those are the two things that it must satisfy. So if your potential function looks like that, then your auxiliary function is going to look like that. And again, the proof proceeds by linear programming bounds. So if you have any chance of being sharp, it had better equal the function and its derivatives at all those points of the lattice. And here, it's potential functions, h auxiliary functions, and h hat looks like that. So it turns out you want h to equal f at all the points of E8 or Leech. You want h hat to be 0 at all the points of E8 or Leech. Those are the two conditions you want, and it turns out you can find these functions. And here's the thing that what we call the Fourier interpolation formula. So one of the key things is to generalize the functions that we found. In the E8 case, we found things which had value 0 and derivative which was at the smallest root at the square root of 2, it had non-zero derivative, but at all the other square roots of 2n, it had 0 derivative, right? Those are the functions found. And more generally, you could say, I'm not going to say, let's suppose I specify square root of 6. I want a function which has zeros at all square root of 2n. It has double 0 at all square root of 2n except square root of 6, and it only has a single 0 at square root of 6. So this gives you a family of functions where you replace square root of 6 by square root of 2n. And it turns out those are the functions that you want. These are what are called basis functions. And the thing that you want is that you want any Schwartz function to be a linear combination, to be essentially determined by its values and derivatives of the function and its Fourier transform at the square roots of 2n. And so we would like this to be that there is some number n0 depending on dimension, such that any Schwartz function is exactly equal to this linear function. That there exists an n0 and functions an, bn, cn, and dn for all n, such that this always happens. And we can prove it for 8 and 8.
The n's are those roughly like those C plus minus.
Yeah, so the C's, exactly. So, right, the ANs are, right, the even eigenfunctions, the BNs are the odd eigenfunctions. Well, yeah, it's actually the AN, yeah, I mean AN plus AN tilde is the even eigenfunction, etc. Yeah, exactly. So, right. So those are the functions we want, and we can prove it for 8 and 24 dimensions. It turns out, once you know that, then well, this H that you want, you just want its, you know what its values and derivatives are at all these points. You know that its values are the same as the potential function, and you know that its derivative and its Fourier transform has values and derivatives 0. So for H, you only have to take the AN and the BN, and not the AN tilde and the BN tilde, which have to do with the Fourier transform. And so, given any F, you can write down the subsidiary H, and all that you have to prove is that if F is completely monotonic, then H, that in fact it satisfies the inequalities. You know that it satisfies the equalities of agreeing with F and having 0 Fourier transform at all these points, and that turns out to be a very painful but doable calculation. So let me stop here and just say, you know, this is rough. I mean, the key thing turns out to be this Fourier interpolation theorem that we can prove, and this we have conjectures for. You know, this is something that should generalize in various degrees to other dimensions, and you know, we don't have proofs for this. We have some evidence. The part that doesn't generalize is, of course, the fact that EA to Leech lattices exist and they satisfy these amazing inequalities and so on. Okay, so let me scroll forward to the. Oh yeah, let me just end with showing you roughly what these, you know, where these functions come from. So you compile all these functions in modular forms into a 2-variable modular form kernel. 2 variables are tau and z, and you get something. You get these matrices involving tau and z. You can write down functions of tau and z, and then you have to do an integral Laplace transform just as in previous case. But you can make it completely explicit and references. Thanks a lot.
So you might have, so these modular forms have nothing to do with the underlying meaning, this moonshine kind of relation between the Q expansions of modular forms.
Not that we know of a priori, but we don't know. I mean, I think there's
for the chemical Leech lattice, it's not this other whatever that J function doesn't. It's not.
I mean, yeah, I don't know if these modular forms have things to do with, you know. I mean, it's possible that there are functions, you know, that show up here that also show up in things like, you know, vertex operator algebras and moonshine.
Yeah.
We don't know. I mean, I think there are a lot more things hiding beneath the surface that we don't know yet. Probably a lot of these things show up in, you know, moonshine-related modular forms, but we just don't know so far.
For instance, for the Leech lattice, I think you would have expected the J function to come. That doesn't.
The J. I mean, you mean just the normal sort of modular J? Yeah, that shows up all over the place. Even in E8, it's going to show up like. Right. So
no, it would of course, but in that case, it was purely the J function which gave you the expansion.
I see.
It's not something so straightforward as that.
You mean?
No, but Q expansion of the J function, which gives you all the dimensions of
I see. Not that we know of a priori, but I think there. So here's an example of something. So for instance, you know, the 196560 roots that you see and the 196884 that you see in the J function, they're obviously related, but can you recover sort of that fact, you know, the 196560 from the J? I mean, by using some fact, you know, from the J function, by using some fact about the sphere packing functions, there are some guesses. So we guessed this is sort of wider conjecture that Emmy and I made at some point. We didn't really formally state it, but here was this sort of point. So there are linear programming bounds for spherical codes, and in the spherical code case, there's a kissing number problem, and that is also optimized by the Leech lattice, and you get exactly 196560. And so our conjecture was that the compact things that you would get, 196560, that would come from a sphere packing auxiliary function. that, there was a way to combine, to sort of peel off the first number of 196,560 roots from the auxiliary function that you see, this phi 0, for instance, that you see in Marina's proof, and that the next one, the next one that you would see for square root 4, that and the square root 2 one could be combined to give the next shell, the number of points there, and so on. So you could see the entire theta function for Leech, for instance, from this sequence of functions. That we haven't even explored. I mean, it's possible that that's doable. We don't know. I mean, so I think there are a lot more, sort of coincidences which are not really numerical coincidences hiding beneath the surface. But we sort of, I mean, this was our priority, and certainly we will be happy to think about those things in the future.
Anything special about 6 dimensions?
In 6 dimensions. I mean, we expect E6 to be the densest sphere packing. Beyond that, I think, in terms of, so at some point we did a numerical study of things like energy minimization for low dimensional things. We looked at periodic configurations, small number of, small periods. So, and we got some very interesting results. So I don't remember offhand what E6 looks like, but it turns out that on one end you get E6, on the other end you get its dual, and in the middle you get something completely different, if I remember correctly. So we had a lot of numerical experimentation in low dimensions, which may be interesting for physicists to look at.
Yeah, Sid.
You might have said this at some point, but on the one hand, it seemed like your linear programming bounds was a statement about Fourier transforms in the radial direction. And then you connected it to modular forms. Can you say something about what the connection really is? Can you see some transformation properties of modular forms or something emerge from?
So I think I think the connection from modular forms came precisely because once you do, the linear programming bounds gave you some information about what f and its Fourier transform, what inequalities they had to satisfy. And when the idea of using modular forms was because you somehow wanted to connect this property of f and f hat to some sort of transformation property of Gaussians, for instance, and that if you write down sort of e to the pi r squared c, that tells you roughly that you should have this modularity property. But a priori, I don't know why linear programming. So let me just say that linear programming bounds are not the end of the story. So many people have. So there are linear programming bounds only use 2-point information, and a priori, that shouldn't necessarily give you something which is shouldn't. So we expect that there are sort of 3-point bounds and 4-point bounds which improve in general dimensions, not in these dimensions, but and in many cases people have worked out these higher point bounds which involve semi-definite programming, and numerically they've gotten small improvements and so on. So they're not the end of the story yet. You can ask the question of what's sort of the dual problem to semi-definite programming bounds, and how could you connect that to, maybe they connect to something like Siegel modular forms because you're using sort of 3-point information, so they're genus 2 Siegel modular forms, genus 3 Siegel modular forms, and that's something that I've periodically thought about, and other people have also, but nobody sort of made a similar sort of theoretical breakthrough like that way.
Thanks.
Other questions? If not, let's thank Abhinav again.